talking here about ways of matching generalizations.
First, I'm already very touched to be talking in this building. I was still an undergraduate. Where is Martin? I was still an undergraduate in at the 76 math programming meeting, so I didn't have the occasion to speak here. I'm actually surprised it was here. Are you sure? Was it really?
But this room, this building.
Yeah, okay. I used to come here to listen to others, and maybe my only chance to speak here would have been at my thesis defense, because that used to be here. I came here to András's actually, but it was just rebuilt when I had my thesis defense, so I didn't speak there either. So, well, of course, more importantly than the building, I am very honored to be invited to the meetings. All the three reasons that Eva mentioned are true for me too. I also learned most of the things I know about the subject from András, and I have also a fourth one, that the subjects on which András started to speak to me and to put questions about were about the Hungarian method, alternating path, and generalizations of this. So part of my talk will be remembering those things, and I would also like to speak to you about some other things. So ways to matching generalizations. I would like to take you to some tour around some generalizations of matchings alternating paths. So I will take out of the Hungarian method what Professor Kuhn called the König part of the Hungarian method. Well, here is a little city made out of such ways, or to say paths. And we'll make a little tour. That's not as quickly as that, but I can slow it down. Okay, so here's the 50-year-old, and if you put some kind of candle-like vertices on it, it looks like a birthday cake. There are 50 of it. I will spoil it now. Let's put it into a graph. So it's part, this alternating path is part of the graph now. And I will spoil it even more, and I put a new vertex to the graph, and I join the new vertex to everything, to all the other vertices. Now, this graph has a matching. The red edges all along the talk will be a matching, not necessarily perfect matching, and the blue ones just ordinary edges of the graph. So this new vertex I join with red edges, so this is not the matching, this is an inception. The edges from x naught can be read without me forming a matching. So I join x naught with red edges to all the unsaturated vertices by the matching. So to all the vertices that are not covered by the matching, and with blue edges to all those which are covered by some edge of the matching. I even put weights now on the edges, +1 on the blue ones, so on non-matching edges, and from x naught to the saturated vertices I put weight 1, and on the red ones we put weight -1. Now we didn't do much, we can reformulate to another language now the problem of finding an augmenting alternating path in this graph. And this language is, we are looking for a cycle of negative total weight. Negative total weight, because the only chance for a path, for a cycle to be negative is to go through x naught, that's the only vertex which contains two negative edges incident to it, and otherwise to be alternating. So an alternating path in this new graph becomes a negative cycle and conversely. This is not much. Let's see the whole text. That's part of it. And well, this is just a reformulation to another language, but it can lead further. So I just repeat here what we did on the previous transparency, and now we have another cycle in another graph where red doesn't mean a matching anymore, but you have edges of weight -1 and some others of weight +1. And this is a negative cycle, so in +-1 weighted graphs you can have a negative cycle. Now these negative cycles are strictly related to some kinds of subgraphs to some factorization problems that were introduced by Jack Edmonds, and one of them, the one which is most closely related to this, by Guan, with the non-polynomial algorithm, the Chinese postman problem. And Jack and Ellis Johnson generalized the Blossom algorithm to this case. Well, I will not state the Chinese postman problem and the generalization T-joint, which Edmonds and Johnson were treated. I will speak about odd degree subgraphs. This was actually the problem that after a seminar András told me, the odd degree subgraphs, they were working on it with Eva Tardos, and through a sequence of results, they proved the minimax theorem. They proved the minimax theorem for it, which, that there existed minimax theorem, the first proved by Edmonds and Johnson, and then a sharpening series of minimax theorems. But even though these odd subgraphs generalized matchings, these results didn't contain directly Berger and Tutt's formula. So the motivation for András and Eva was to have a theorem in a tighter form which directly contains the Berger-Tutt formula. But they could prove such a theorem using the previous results, and the proof was quite complicated. They didn't feel like writing it up because it was quite long. And so that's why after the seminar András has asked me, well, here you want to work, well, here's the problem. On circuits, here's a minimax theorem. I won't state the minimax theorem, and we would like a simpler proof for it. Now, if you hear such a problem, you can rediscover one statement that an odd circuit subgraph has minimum cardinality if and only if putting weights -1 on the edges in the subgraph and +1 outside, you don't have a negative circuit. And if you have a negative circuit, you switch. So this is the generalization of the alternating path that we looked. Maybe better to have a pointer. I'm looking for the good. It's invisible. And if you know this, then you have an idea how to prove any kind of theorem, whatever. We don't need to know here what this minimax theorem was. Actually, it suggested such a reduction, such a proof by induction. And the idea is the following: until you have vertices whose distance is the shortest path in your graph is non-negative, you shrink that pair of vertices. It remains. It won't have. If your odd circuit subgraph was if the weighting of your cycle, if the weight of your cycle was non-negative, even after contracting, after identifying vertices that are at non-negative distance, you won't have a negative cycle. And indeed, this induction works. The induction step for proving the statement that was asked, this step does work, and quite easily. The problem is the starting step, that if you don't have, if the distance of any two vertices is negative, then the statement is not, it's not evident what are those graphs, and it's not evident to prove the statement of the theorem of Franken-Tardos. So after a first happy first enthusiasm about this good induction step, the starting step was very difficult to find and had to wait. So I will use two definitions. First, rather definition and the notation. The graph is called conservative if there is no cycle of negative weight, negative total weight. There is no cycle whose total weight, sum of weights is negative, and the second is the distance from fixed vertex. We'll, in the following 5 minutes, fix a vertex in the graph and look at the distances from that fixed vertex. Lambda u will be the minimum weight of an x naught from the fixed vertex to any arbitrary vertex u. Okay, and then we started to play. So I won't be able to write in my CV that I ever was a member of the English group. That's very recent, so I don't know whether I still have a chance to be a member of it. But maybe András will not protest that those meetings at his apartment those days were maybe a precursor of the English group. So we worked at different places, András at Taki with Eva, and I worked at Stocky. When I became, well, after all this, I was an SP, I was a graduate student. So when all these things happened with the distances, we met in his apartment. We always had a different subject, and we started to play. András had an idea, a conjecture, that if we take an arbitrary graph, plus minus one weighted graph, which doesn't have a negative circle, and we put the vertices into levels, like the graph which is here. If you put the vertices into levels according to their distance from x0, you get the following. You get minus 1 up there, 0 x0, and some other vertices that are at distance 0, and then there are vertices at distance minus 1 and minus 2. And then we started, so András told us that well, if you take the lowest level, there will be always one negative edge going into the vertices there. That is actually, you can quite easily prove. And then you take the next level, the minus 1 and minus 2 level, and you look at the components now of the graph. Yeah, the colors are different on the screen, but maybe you can see that there are two components of the union of the minus 1 and minus 2 level, and there's also one negative edge in both. I will use the pointer, so there's one of the components of this is the negative edge, and for the other one, this one. So there's one negative edge, and so on, at the level 0 or so, the components have at most one negative edge going into it. Well, in a dual graph, so now I will do the same on the dual of this graph, and x0 will be the infinite phase. So infinite phase is x0, and we will look at the distances from the infinite phase. You can check that at level minus 2, at distance minus 2 from the infinite phase, and now you go through phases, and when you cross a red edge, that counts as minus 1. When you cross a blue edge, that counts like plus 1. And so these are the phases that can be reached with a path of weight minus 2, and they have one negative edge in their boundary, and now you see the vertex, the union of the components that are at distance minus 1 and minus 2 from the infinite phase. They also have one negative edge. So it seemed to be true each time we drew it, and actually the first thing that started to work with it was that if this conjecture were true, it followed that the graphs, which are starting steps of that induction, so graphs in which every vertex bipartite is the condition there, but I will tell you that's not really an essential condition. The graphs in which all the distances are negative are just forests, with all weights, with all edges having negative weights, minus 1 weights. Bipartite is not really essential since with respect to distances and cycles, if you have an arbitrary graph and so you subdivide every edge into 2, you get a bipartite graph, and all the weights of the cycles and paths will be exactly double. So you don't change much by reducing it to a bipartite graph. Of course, you can state statements for arbitrary graphs, but they will be slightly more complicated. So that's why I state here only for bipartite graphs, noticing that the condition is not essential. And so first this could be proved, and so the theorem of Frank and Tarbes could be proved. I generously got to be a co-author of that result, and then also the conjecture of András could be proved. Now this there was another lucky coincidence when I proved this theorem, and it was the manuscript of the robust London book, which contained a problem about T-joins. That there is no generalization known of the Galilei-Edmonds decomposition and other results of mention theory to T-joins. And it turned out that it is actually this theorem, which is the Galley-Edmonds theorem for T-chance for odd forest or odd degree subgraphs, and some other theorems about matching covered graphs and basic partition that they have could be also proved using this theorem. And actually I found it a bit secret at this general level. Some cases that are different, that are separated from matchings, become united in this context of T-charts. It also got other applications by András and Szigeti, András Sebő and Szigeti about packings, integer packings of cuts, or cuts containing one negative edge, or packing paths. Okay, now I switch to the next path, the next subject, about various degree constrained bidirected graphs, about which I learned a year later meeting Jack Edmonds in Bonn. He explained me about bidirected graphs and about a bidirected graph is a graph where every edge has signs in the two endpoints, plus and minus signs. And paths in a bidirected graph have to alternate in signs when they go through a vertex. Now, you can restrict yourself. It's not much of a specialization by supposing only red and here we have black, red and black edges, because you can put new vertices. If an edge has two different endpoints, one plus and one minus, you can put a new vertex and have the same signs at both endpoints. On the other hand, if you are not dealing anymore with matchings but more general factors, you will have in your improving paths, and that's well known already for proofs of Tutt's theorem and so on, that the improving paths that you get are not only alternating paths, but they can be alternating boards. They can go several times to vertices, like on the picture. I don't want to go into details. Let me just mention that a reason why the Hungarian method works so well, the alternating path method works so well, is that there's transitivity of reachability with an alternating path. If you can reach a vertex B from vertex A and a vertex C from a vertex B, then you can also reach A from A, you can reach C in a bipartite graph. So there's transitivity. Now for bidirected graphs, it is not true. You see here on the picture bidirected graph, or a red-blue colored graph, and from A to B, there are all paths of all kinds of signs, red-blue and red path, and also from C to B, there are paths of all kinds of signs, but from A to C, there is no path at all. So transitivity is not true, but there's a kind of broken transitivity which is true, and which is the following. If you have a path from A to B, and from B to C, and from B with the opposite sign, you can't necessarily put them together to get one path from A to C. But if you cannot, then something else, which is very good, is true, and you have paths of the opposite sign, also from A to B, and to B to C, and from B to C. So kind of transitivity is still true for these two-colored graphs, and these, again, leads to proofs of structure theorems for p-matchings, and also structure algorithms. A structure algorithm is an algorithm that Lex called this morning brute force algorithm, keeping a kind of several objects that are candidates for being optimal at hand, and then either proving that they're not optimal and improving the size of an optimal primal solution, or improving the structure, and which certifies that all your objects are optimal. So these, such a structure algorithm, so brute force algorithm for p-matchings, can be proved using this transitivity statement. Now, let's go to a little bit further from matchings. You have, let's look at the following problem. You have a graph, and you're looking for a stable set of fixed size that covers a maximum number of edges. So a set of fixed size that covers the maximum number of edges. Of course, this contains the vertex cover problem, so it's then hard. You can't, you don't want to solve it. But for line graphs, it's the generalization of the matching problem. It's vertex cover. Vertex cover is the complement of the stable set. The stable set is a matching in a line graph. So this problem is a generalization of matchings, and it's not completely, it's not evident. So it's a real generalization of the matching problem. So what is this generalization? Now, if you delete a set in a line graph, the number of edges which remain is the number of undeleted edges choose 2, which is the number of undeleted edges square minus the number of undeleted edges. If you sum up this number, you will get that it is the sum of the squares of the degrees minus the constant. So this is equivalent to minimizing. This is equivalent to minimizing the sum of the squares in a subgraph of fixed cardinality. And now, the reason I am speaking about this too is that here alternating paths come in a little bit more general way. It's no more true, like for B matchings or matchings, that if your matching or generalization is not optimal, then you have a path, or you have a degree sequence that differs from the old degree sequence only in 2 vertices. Then there is a better solution differing from the old one only in 2 vertices. Here you would need 4 vertices, so you need pairs of alternating paths. Here is an example where on the left example, oh yeah, you have twice the same. 14, the score, so the red edges mean the factor, and you want to minimize the sum of the squares. So the sum of the squares, you have the vertices of degree 2, that's 4 times 3, 4 times 3 for this triangle, and so that's 12, and 12 plus 1 plus 1, so we have 14. But there's a better solution, 12. Of course, the average would be good, but the graph doesn't let you to have the average all the time. Anyway, it is true that either alternating paths or pairs of alternating paths, one of which decreases the size, the other increases, always are good, and this has been generalized actually to jump systems by Murata recently, so we can do all this at the level of jump system. Well, here's another example. Now you just to make sure that you understand what it means to hit in a line graph, what it means in terms of the original graph now. If I choose this edge, it hits 4 edges of the line graph. If I choose these 3, you get 24, and now you have 50 edges of the line graph hit. Well, we want to compute this. Could we make a nice birthday cake too? Let's go, rather than computing the number of edges hit, to another problem, to independent sets. If you take independent sets in the line graph of the graph, this is what you get. You get an alternating path with a smaller number, with k minus 1 vertices in the actual stable set, and k vertices that you can put in the stable set without getting an edge, so that it remains still a stable set. Now, this picture, you get, well, in some graphs, if you want to maximize the stable sets, also in matrix, in the matrix intersection problem, you get a similar picture, and also for posets, for Dilbert's theorem. Of course, you just have to translate what the proof through curling theorem means. Anyway, there's something else which is common between all these, and and what is common in all these is that if you want to partition, if you want to take a union of stable sets or independent sets of metroid and so on, you get also similar theorems. You get Green-Kleidman's theorem for stable sets, and you get a form of elements partition theorem for metroids. If you write it in a form, maximize the union of k stable sets in a graph. They are all theorems of the same form. Actually, Green-Kleidman's theorem is usually put in another form, but that's just to hide the similarity. You can all these theorems are just state that the maximum union of k, well, I stated for anti-chains, the maximum union of k anti-chains is equal to the minimum of the cardinality of x plus k times the number of chains you have in a set of chains covering v minus x. So it's exactly the same form. If you replace anti-chains by independent sets of metric, you get the corresponding form of Edmond's partition theorem. For anti-chains, there are some extensions, as I mentioned there, by Fraunhofer and Hartmann. This latter is a recent result, actually, for acyclic graphs, in which this picture that you have about stable sets arises in a little bit more complicated way. Again, levels. Since you have k stable sets, you have to push not only exchange between two stable sets, but also consider your k stable set and push vertices through levels. So that's also a generalization of the alternating path method. Anyway, I make a little detour to a conjecture of lineal, which has a version by Berge, and which Lex likes somewhat because he put it in his book, but he doesn't like enough to, it was not among the problems that were mentioned this morning. It's problem 5 in Lex's book. It's about an inequality between the maximum k-chromatic subgraph and this quantity that arose in Green and Kleidman's theorem. Now for k equal 1, this is proved by, this is Dallay-Milgram theorem. That is a very well-known theorem from 60, that the maximum stable set is bigger than the minimum cardinality of a partition into paths. It has an orthogonal version that András and Irith in their survey paper called orthogonal version, that there exists a path partition and you can choose one vertex from each path in such a way that the vertices you have chosen form a stable set. It has strong versions, so it has an orthogonal version and a strong version, I don't mean strong in terms of strength of the theorem, though it looks like it's much more difficult since it has been proved recently, only 40 years later, though it has been a conjecture since 1962. And the strong version is mechanically the same statement, and there are many statements. Actually, there's a branch of theorems, many of them proved by Adrian Bondi, where you you suppose the graph is strongly connected, and you replace path by cycle and partition by cover, and you get again a true theorem. Now, in this conjecture has been proved with surprising new and very elegant ideas, though not very complicated, by Besse and Thomasse recently in 2003. So they proved that in a strongly connected graph, alpha is always bigger than the minimum cover by cycles. Now, what is the reason I made this detour? It's quite frustrating that sorry, I forgot to say something. The orthogonal and strong version also follows from Besse and Thomas's theorem, because they actually proved the minimax theorem, and when you have equality in that minimax theorem, you have orthogonality. Now, if you have k arbitrary, this orthogonal version is a conjecture of Berge. I'm actually not sure, maybe this is the problem 5 in Lex's book, the conjecture of Berge, that you can choose one vertex in, you you have a partition into cycles, and you can choose one vertex on each, so that they form a stable set. And this minimax, the strong version of this, of strongly connected graphs, if you replace paths by cycles and partitions by covers, so the version that should be more difficult can be proved. That's true. That's true. You can prove with using tools of Bessie-Thomas and some polyhedra, so the integer decomposition property. Some kind of particular stable sets have the integer decomposition property, and therefore this strongly connected version for cycles of the theorem is true. And the other one, the one which is the generalization of Milgram's theorem, remains open. Okay. I'm almost finished. I would like just to mention, without saying much, two other examples. One from polyhedral combinatorics, test sets. This is about capturing, I don't know whether historically test sets came from the Hungarian method of alternating paths, but the fact of alternating paths and improving paths for matchings and many other combinatorial theorems can be put in the following form. If there exists a better solution, if there exists a better matching, then there is also one which covers two more vertices. Now this has been generalized to arbitrary linear programs, and integer programmers use it to design efficient algorithms for integer programming problems, especially if you want to solve the same problem. You want to solve many problems with the same matrix A. So these test sets depend only on the matrix A and can be used for arbitrary right-hand sides. I don't want to skip some things. And another generalization in this abstract direction is jump systems. A jump system is a set of vectors which seizes which captures the property of degree sequences, and well, let's give the examples. Degree sequences, well, maybe one example I should mention, the one-dimensional jump system. One-dimensional jump systems are sets of numbers with the property that you don't have consecutive holes. You can have consecutive non-elements of your one-dimensional jump system. The red ones are those which are not elements of this one-dimensional jump system. So you can have a starting sequence and an ending sequence of non-elements, but in between the first and last element of the jump system you have only one element holes. These are the one-dimensional jump systems. Another example of jump systems is subsets of T covered by T-path packings. Lex spoke about T-path packings this morning. So the set of T-covered vertices of T-path packings forms also a jump system, which follows from Schreifer's proof of Mother's theorem, as proved by really Ben-Navin and myself observed actually from the proof of Lex. Now, jump system intersection theorems were raised by some basic results of Lovász in 95. Well, the first result, even if it was not stated so, yes, even if it was not stated so, was by Kormezsos. Kormezsos developed an Edmonds-type algorithm for the intersection of degree sequences with such a general box, with the Cartesian product of one-dimensional jump systems. And these are called general factors. Lovász then generalized these to some results of Lovász from 72 actually describe the basic results, type results for these general factors. But the algorithmic, polynomial algorithm for this problem was overlooked and was then solved by Kormezsos many years later. These could be reduced actually after Kormezsos these results were proved, it could be realized that using Lovaas's results, using Lovaas, a very simple lemma of Lovaas, these general factors can be reduced to upper and lower bounds and parity constraints, and this can be done also at the level of jump systems. So Lovaas's result on the intersection of jump systems with a box can be extended to jump systems intersected with box and parity constraints. And I'm done. We have not been as quick as here. We could go, I didn't have time to prepare eating the cake. Anyway, it would be good to have such celebrations more often than every 50 years, and we would have a chance to participate in more than one. Thank you very much.
Do you have any questions?